Hi, I'm Matthias Beck. I'm one of the authors of Computing the Continuous Discretely. And in this video, we will continue to discuss integer point transforms of rational cones. In particular, I would like to say something about the complexity of these generating functions, and then give some remarks about decomposing integer point transforms through a triangulation approach. Our starting point is a continuation of the previous video, is this theorem. You've seen this theorem in action in several examples in the previous video. We stated here in general. So suppose you're in dimension D, you have a simplicial d-dimensional cone. So that means I have d linearly independent generators, W1 through WD. I can choose them to have integer coordinates. Then I can shift my cone by some real vector v if I want to. And we have the following formula for the integer point transform of the shifted cone v plus k. Namely, it's a rational function. In the numerator is the integer point transform of the shifted half-open parallelepiped spanned by the generators. We call this pi in this case. So this is again a linear combination of the generators W1 through WD, but now my coefficients are between 0 and 1, 1 not included. We will shift that parallelepiped also by v, and then list the integer points in it as Laurent monomials. So this is the sigma function for v plus pi. And in the denominator we have a product 1 minus z to each generator. My first goal now is to give more examples of this theorem for specific cones. And I want you to pay attention to how the rational function that describes this integer point transform changes as I change my cone. So my first example is mainly to remind you of the techniques that we used in the previous video. So I have a cone generated by two vectors in two dimensions. One generator is 1, 1, and the other generator is 3, 1, so it's this vector here. To write down the integer point transform, on the one hand, in the denominator over here, you see the vector 1, 1 encoded as a monomial, and then the vector 3, 1 encoded as a monomial. So these are the generators. And then up on top, you see the points in this fundamental parallelepiped encoded. Remember, this is half open, so in this case, I have 2 points in here. It's the point 0, 0, and the point 2, 1. And so 0, 0 gets encoded into the monomial constant 1, and 2, 1 is encoded in this monomial over here. So now let's change the second generator, 3, 1, and I want you to notice what happens. Okay, so I left the first generator as is, and my second generator is now, I guess, 10, 1. I hope you can see the fundamental parallelepiped here. Yeah, the effect of this change is I have to consider more points in this fundamental parallelepiped. Again, my generators appear in the denominator of the rational function version of the integer point transform. But now you can see that my denominator becomes larger because I have more terms. I guess I have 9 terms here. Once more, let's change this cone just slightly. Again, I will change the second generator and now put this generator on the x-axis. So I will use the generator 1, 0. You might say, this is almost the same cone, but you can see the arithmetic of this cone is quite different. So if you remember from the previous video, so now I'm in the situation where I have two generators that form a z-basis of the integer point in R2. Trace this back, so this means that my half-open fundamental pipette only contains the origin, and you can see this reflected in the rational generating function that belongs to this cone. There's a single one in the numerator. One message I want to convey here is that these two cones, although if you want geometrically they seem close, arithmetically they're quite different. And the arithmetic is somehow encoded in the fundamental parallel pipette. If you concentrate on the fundamental pipette in this example and in my third example, you see that in this third example it becomes much smaller, and this gets reflected in the form of the integer point transform. I want to make a second remark. So far, all of our cones had the origin as the apex, but in my initial theorem there was a possible shift vector, and I want to show you one example where this happens. So we're back to the first example where my generators are 1, 1 and 3, 1. Let me now show you what happens when you shift the whole cone by a fixed vector. We use the vector 1/2, 0. So this is my shift vector that in my theorem is called V. I hope you can see that my generators stay the same. They're now just in a funny place in this picture. So here's the generator 1, 1, and here's the generator 3, 1. Let me remind you in my theorem that the effect this has on the formulas for the integer point transform is in the numerator polynomial. Generally, this will be a Laurent polynomial. So what we're going to have to do is we have to also shift the fundamental parallel pipette. So let's do that. You can see this in this picture. And so the effect is that the points that get encoded in the fundamental parallel pipette now got shifted. In the previous example, these points were the origin and the point 2, 1. And now it's the point 2, 1 and 3, 1. And you can see them reflected in these monomials in the numerator. I'd like you to notice that the number of terms is the same. That's not an accident. We will talk about this in a moment. But the nature of the terms has certainly changed. So let's go back to the general theorem. Here it is. And I would like to ask the following question. What's the complexity of this integer point transform? You can think of this as the sort of question you'd ask if you'd have to write an algorithm to teach a computer how to compute these rational functions. Okay, so the input here are my generators, W1 through WD, and this apex V. So the denominator is given to you. I assume that I know this data. And so I hope you can see from this theorem that the complexity of this integer point transform is entirely in the numerator. So this is a Laurent polynomial in d variables. The first thing we should note is the number of terms is, of course, the number of integer points in this shifted parallel pipette. Well, it's a half-open parallel pipette. And so I will now give you a sort of heuristic argument that this number of integer point is actually the volume. And of course, the volume is invariant under translation. So this complexity gets measured by the volume of pi. And if you now go back to your linear algebra course, there you hopefully learned that this volume is given by the determinant of your generator. So I'm thinking about constructing a matrix. This is a D by D matrix out of these generators. Compute the determinant and take the absolute value that is the volume. Why is this true? Well, again, let me give you just a schematic sort of idea. So if I think of one of those half-open parallelepiped, I can now tile the whole space with translates of this parallelepiped. And in fact, I can do that in a non-overlapping fashion because the parallelepipeds are half open. And so I claim, so if you think that my tiling also has to cover all of ZD and my generators, no matter what vertex down here is, my generators are integer vectors. That means in each translate I see a copy of the integer points in the original parallelepiped, and I claim because of this the number of integer points has to be the volume. At any rate, I invite you now to look back at our examples we've had so far in this video and in the previous one and realize that the complexity in each example can be expressed in a very concrete way by the volume of the fundamental parallelepiped, or alternatively by the determinant of the matrix constructed by the generators. Let me finish this video with a remark, and that is give you an idea of why we're interested in shifting a rational cone by a quite possibly irrational vector. Again, it's important that the generators of my cones are still integer vectors, but the apex is a general vector with real entries. And this motivation comes from triangulation. So in 2 dimensions, it's a little funny because all cones in 2 dimensions are simplicial, but I hope the underlying message will be clear. So let me assume I have one of my cones from before, so it's a cone generated by 1, 1, and then this vector 10, 1. And let's say I triangulate this into 3 cones, let's say like this. And then for some reason or other, I don't quite know how to compute the generating function of my original cone, but I can somehow compute that from the generating functions of my smaller cones. But now you should stop me in saying I actually over-counted, I over-enumerated, and so I have to subtract, the integer point transforms of intersections. And then add back in what I subtracted too much. So this is sort of an inclusion-exclusion way. In general, this is not a problem. In general, let's say my smaller cones form a triangulation. That means their intersections will be simplicial again. I can compute all these generating functions, but it might be computationally expensive. So let me show you a trick. I will take this whole setup. I will take my large cone and the small cones. I think of all the possible hyperplanes that you see here, and I will shift them by the same vector in such a way that I have not lost any integer point in the big cone. Let me show you happened here. And I'm moving all my bounding hyperplanes, all the facet of the small cones, in such a way that they don't intersect the integer lattice. What effect this has is I can compute the integer point transform of k by saying, hey, this is really the integer point transform of my shifted cone. So I think of this little shift here as my vector v. And the effect this has is, well, I will shift each of my smaller cones, add up the integer point transforms, but because none of them have any integer points on their boundary, I do not have to use inclusion-exclusion. I can stop here. If you think back to my complexity argumentation, what I've done here is seemingly I've made things more complicated. I shifted each of my individual cones by a vector v. So this is a price I'm paying in exchange for not having to do inclusion-exclusion. But what I'd like you to notice is that the complexity of these three integer point transforms is the same as the complexity of the integer point transforms of the original cones k1, k2, and k3. My rational generating functions might now look different because I shifted each cone, but the complexity, the number of terms in the numerator of each rational function, stayed invariant. This is a trick that you can use both in terms of computation. If you have, for example, a non-simplicial cone in higher dimensions, use a triangulation. This allows you to get around inclusion-exclusion. But we will also use this trick for proving theorems, simply because some theorems are easier to prove for simplicial cones. And we will see an application of this setup where we can use the fact that we have a variant of a certain theorem in a simplicial case through this sum here, where we don't need inclusion-exclusion. We can deduce the theorem in the general case.